Well, hello, everybody. Let me introduce to you Yining Zhang from University of Colorado at Boulder, and he's going to talk to us about Hodge decomposition of string topology.
All right, thank you very much. Thank you for the invitation, and very glad to talk in here. And unfortunately, I cannot show up in Purdue, so yeah, hopefully I can still meet some of you in the near future. Okay, so what I'm going to talk about is joint work with Yuri Berest and Ajay Ramadoss, and it's about Hodge decomposition of string topology. So let's just get started with some backgrounds. Okay. So the first part is string topology. So just some background on string topology. I believe one of my friends, Florian Neff, gave a talk about string topology maybe a month ago. So he probably also introduced most of the terminologies in string topology. So I just briefly recall something I will use in my talk. So, all right. So let X be a closed oriented manifold of the dimension D. And throughout this talk, we always work on the rational coefficients or the homology, cohomology with coefficients in rational numbers. Okay, so the main object in the string topology is the free loop space, which is just the mapping space from S1 to your manifold. So that's the main object in string topology. So roughly speaking, you can think about string topology is just all algebraic topologies related to this free loop space. And okay, so it's free loop space. There's no base point. The only thing you need to be careful is that even though there's no base point, but for each loop, for each free loop, so at each object or each element in this mapping space, there's a marked point, which is the image of 0 or 1 in your S1. Okay, so you do have for each free loop, you do have a mark point. So actually, this mark point gives you an evaluation map from the free loop space to your underlying manifold, right? You just send each loop to its base marked point, okay? And okay, so there are some algebraic structures related to the free loop space. The first one I want to introduce is so-called the loop product. So of course, this is all those things are discovered by Charles and Sullivan. Okay, so what is a loop product? So let me just first write down. A loop product is a product on the homology of the free loop space. So as I mentioned, I will use rational coefficients throughout the talk. But it has some degree. So it's a product of degree minus D, okay? And it's commutative associative product on the homology of free loop space. And the idea of this loop product, you can think about that. I pick a family of two families of free loops, and I can use this evaluation map. Just basically, you pick one family, you map to its to their marked points, so you get a right, and then you pick another family of free loops and map to their marked points, and then you transversely intersect them on your manifold, right? And then you just, on those intersect marked points, you just travel along the first loop, then the second loop. So that's roughly the idea of this loop product. And because of this transversal intersection is of degree minus D, so this is also a product of degree minus D. Okay, that's the first algebraic operation we are talking about is loop product on the homology of free loop space. Okay. And now there is also an S1 action on the free loop space, right? So the action is just you acting on the domain on the S1. So you're just rotating the domain, okay? And because of this action, we can look at the homotopy quotient of this free loop space. And also we can look at the S1 equivalent homology of the free loop space, just the homology of this homotopy quotient. Okay. And the idea is that you can think about what is this quotient is that, as I mentioned before, so for each free loop, you have a mark point, which is the image of 0 on S1. But when you're basically rotating this, you just change the 0 among S1. And after you quotient that, you can basically think about, I just don't have the information about the marked point because I quotient by the S1 action, okay? So the idea in here, you can just think about, I just get those loops without marked points, okay? And also you have this homotopy quotient, you get a S1 fiber sequence, a fiber bundle, so you get a decent sequence, right? And basically connecting the homology of free loop space and the homology of S1 equivalent homology of free loop space. So again, as I mentioned, I always use rational coefficients, so let me just skip those Q's. So get this long exact sequence connecting homology of free loop space and S1 equivalent homology of free loop space. And there are two maps I want to mention here. So the first map is the map from the regular homology to S1 equivalent homology. And I think in Charles and Sullivan's paper, they use E to denote that. And also there's another map, this from S1 equivalent homology to regular homology with degree +1, they use M to denote it. As I mentioned that, you can think about this E map is erasing the marked point, right? Because just I mentioned that this homotopy quotient is just the same thing about forgetting the marked point, right? So E is erasing. But how about M? M is actually marking, right? Marking the marked point. Because S1, so you can mark any place among your S1, so that's why you will increase the degree by 1. And now there is the second algebraic structure we want to talk about in string topology, is so-called a string bracket. Again, it's discovered by Charles and Sullivan. Okay, so what it is? So I can just pick two classes on my S1 equivalent homology of the free loop space, and I can define this operation given by the following formula. Put a plus minus sign here. So I can send them to the S1 to the regular homology of free loop space, right? Using this M map, and I can take the loop product, right? And then I just erase the marked point, right? So this gives me back to a class in the S1 equivalent homology of free loop space. And this operation was proved by Charles and Sullivan, is actually a Lie bracket of degree 2 minus d, right? Because you have two M maps, those two M maps will increase the degree by 2, and the loop product will decrease the degree by d. So totally, and E will not change the degree. So totally, you will get a Lie bracket of degree 2 minus d. Okay. And so this is the second operation we are looking at. And so this is a Lie bracket on the S1 equivalent homology of free loop space. And for some technical reason, actually, we are looking, not just look at the S1 equivalent homology, we look at a reduced version. So we'll look at actually the reduced S1 equivalent homology. So it's actually given by the following definition. Because of this homotopy quotient, you have another fiber sequence with fiber, which the fiber is the free loop space and the base is actually a BS1. So, yeah. So we define the reduced S1 equivalent homology to be the kernel from the S1 equivalent homology to the homology of BS1. Okay. So actually, that's what we are looking at. But of course, you still have the this string bracket on the reduced S1 equivalent homology. Right.
I would have guessed that like reduced equivariant homology would be like not the kernel and homology level, but like the homology of the cone. Is that different?
The homology of the kernel.
Or like you're saying you have a G space, and so you have a map to BG, and then you're saying take the kernel of that map, and I would say that you would want like the kernel at the chain level, or you know, you'd want like something more homotopy invariant. You'd want to like take.
Yeah, I think this definition very algebraic. I think, yeah, I think maybe I'm not like answer a question precisely. I think there's like two similar definitions. This, I think this, let's call this like a reduced S1 equivalent homology. Maybe another thing is that you want to, they probably have a something called a relative S1 equivalent homology. Actually, is relative to the constant loop. Is that maybe that what you're asking?
Or no, I guess what I was saying, or maybe what I was saying was I would just think it would be relative homology of BS1 rel LX instead of the kernel. But maybe something is injective or something.
Yeah, yeah.
Is this map surjective that you're taking the kernel of? Is that always surjective for some reason?
No, I'm not sure. I just used this definition actually. Yeah.
Yeah,
So,
I don't know.
yeah. Actually, this can be explained in the like talk. Actually, we'll only do for like the algebraic model of this thing. So actually, this is related to the reduced cyclic homology. Yeah.
Or just move on. Whatever, it's fine.
Yeah, but for like basically, this is very related to reduced cyclic homology. So reduced cyclic homology is basically you can think about just take off all the copy of K on even degree, and this is roughly the same analog in here.
But is this a homotopy invariant of X?
So you are thinking about this reduced is not a homotopy invariant.
Oh yes, it probably is. Okay, never mind.
Yeah, you have the fiber sequence, right?
Yeah. Okay.
Anyway, I mean.
Yeah.
I can explain why we use the reduced version on algebraic side, but I cannot explain on topology side because we just use others result. All right, any other questions? All right, so let's move on. So, okay, so I basically talk about at least the background of half of my title. So now it's the decomposition part. So this decomposition, I want to record some results by the following people. So it's Regalia and Fyodorovich and Gada. So what they did is that first you can consider the unfold carving on your circle. You can consider the unfold carving on your circle. Basically, just rotate your circle n times. And actually, by the argument, we actually this carving will induce a power map, or maybe more precisely, probably is an atom operation on the reduced S1 equivalent homology. Again, we'll just use the rational coefficients. And in particular, they show that if X is one connected, simply connected, we have a Hodge type decomposition on the S1 equivalent homology. Reduced. Okay. So let me explain what it is. So for each piece, this Hodge piece is actually the common eigenspace of those phi with eigenvalue n to the p. Okay. So each Hodge piece is actually just put definition is a common eigenspace of those phi to the n, not phi n, should not say phi to n, with eigenvalue n to the p. Okay, so that's their result. So now what do we have? So we on this S1 equivalent homology or reduced S1 equivalent homology, we have first we have string bracket, so it's a Lie bracket, and now we have a Hodge type decomposition, right? So this decomposition. So it's very natural to ask, well, are those two structures compatible with each other? So basically, more precise is that the question is that does the string bracket preserve this decomposition, right? That's very natural to ask. Well, so that's basically the motivation of our work, right? So the answer is, that's basically the, let me just first write down the answer. The answer is yes. If X is rationally elliptic, so that's the condition we need to add, at least for our argument. So what is rationally elliptic means? It just basically means that you look at rational homotopy groups, and so it's basically homotopy group tensor with Q, and the total dimension of rational homotopy groups are finite. Okay, so that's the meaning of rationally elliptic, and our main result is given by the that. So if you bracket a piece, Hodge piece, we keep using rational coefficients. So let me just skip that. With Q's piece, well, actually, you will end up in P plus Q minus 1 piece. So that's our main result. And yeah, and the talk is basically, I try to explain, maybe at least briefly talk about how do we get this result. Okay.
So now we're assuming X is simply connected throughout the whole.
Yeah, simply connected. Yeah. So I just, because if it's not simply connected, you just don't have this decomposition.
I have a question also. Is there any sort of similar decomposition you can do in ordinary homology?
You mean, yes, I think so. Yeah, they also did for the ordinary homology, and yeah.
And the loop product preserves that decomposition as well?
Probably after a little bit of shift on the like Hodge piece. Yeah.
Okay.
Yeah, it's like up to a shift it is preserved. Yeah.
Okay.
Actually, we will use that.
Okay.
But yeah. So, but first when we studied this, we studied this decomposition at least on the cyclic homology level. So
is the cyclic thing a formal consequence of the ordinary case?
Yes. Yeah.
Okay.
Yeah. Because basically, you look at this formula where it is. Yeah. So in this formula, basically, the key part is actually what happens when we take the loop product, right? So yeah, we will do that actually. All right. So yeah. So as I mentioned that what we did is purely algebraic side of this statement. So basically, we did not prove that geometrically or topologically. So what we did is that we find an algebraic model about string bracket or loop product, and then find algebraic models of the decomposition set, and we prove the algebraic version of this statement. Okay, so that's what we did. All right, so the next part is basically I want to talk about some algebraic models.
So I have a quick question. Maybe you'll mention this now, but you said you passed to algebra and you proved this using algebraic models, but then you need your algebraic models to preserve this decomposition as well.
Yes. So what we did is that basically, yeah, we will construct all those product or bracket in terms of cyclic and Hochschild homology, and yeah, we prove that on cyclic homology side. Okay, so let's recall some algebraic models we use. The first thing is that why I need to use the rational coefficient. Probably most of you already know that I need to use some algebraic models from the rational homotopy theory. Okay, so let's, again, in our talk, X is always one connected, but let me just write it down. So X one connected space of finite rational type, and because that was guaranteed by this rational elliptic. So what do I mean by finite rational type? Is just the total dimension of rational cohomology is finite, or rational homology is finite. Okay. So recall that in rational homotopy theory, we have something called Quillen model. Okay. Let me briefly recall what is a Quillen model. So Quillen model is a connected DGLA over the rational number, rational coefficient. I don't want to touch it too much, but basically this Quillen's model can encode all the rational homotopy information of your space. And not only than that, the Chevalier-Ellenberg cochain algebra of this DGLA is actually a Sullivan model, but I don't want to mention that. It's basically, the consequence is that the Chevalier-Ellenberg cochain algebra of Quillen's model is a cochain model of your space, which basically implies that your Lie algebra cohomology with, again, rational coefficient will compute your rational cohomology of your space. Similarly, the Lie algebra homology with rational coefficient will be the rational homology of your space. Okay, but that's a consequence of Quillen's model. And moreover, as I mentioned, that this is a DGLA, so you can compute its homology. Okay, as I did not mention that, but all the DG algebra, DG Lie algebra, in my sense, a differential gradient algebra with with a homology, with a homological gradient. So the differential will decrease the degree by 1. Okay. So the homology of the Quillen's model is actually isomorphic to so-called homotopy Lie algebra. So let me talk about what it is. So homotopy Lie algebra up to a shift is just the rational homotopy group of your space. Okay. So that's Quillen's model. And why I want to talk about Quillen's model is because of the following theorem by Jones and also by Jones and McClear. Theorem, Jones and McClear. So basically, what they talk about is that, as I mentioned, that this Quillen's model is at least a Lie algebra, so you can find its universal enveloping algebra. And the Hochschild homology of UAX, the universal enveloping algebra of Quillen's model, is actually isomorphic to the regular homology of loop space, free loop space, and the cyclic homology of that. UAX will be your S1 equivalent homology of the free loop space. Okay. And moreover, we have this Giesen sequence connecting the ordinary homology of free loop space and the S1 equivalent homology of free loop space. And also we have Cohn's long exact sequence connecting Hochschild and cyclic homology. Actually, they also show that this Giesen sequence will be identified with the Cohn's long exact sequence, which is, just let me recall that. Very similar sequence, you just use this identification. And also we have, recall we have two map, which is E map, erasing the marked point, and M map, which is marking the marked point. And this will be identified with the I and the B map on Cohn's long exact sequence. Okay, so good. So at least we have some algebra models. We have algebra model on the ordinary homology of free loop space, S1 equivalent homology of free loop space. And we also have models for those maps between them. So now the question is that, well, in order to find a model for string bracket, the only thing left is the model, the algebraic model for loop product, right? So if we find the algebraic model for loop product, we get everything we need. So now the next part is find the algebraic models. Just algebraic model for loop product. And also if we find that, we basically got an algebraic model for string breaking. All right. So now, again, because let's just recall the assumption is that X or manifold is one connected, closed and oriented. So we can find its fundamental class. And fundamental class is a top class on the homology, which is actually means that it is at least a class on your Lie algebra homology, because the algebra homology of Quillen's model is just the homology of your space. So this is the fundamental class. And also you can lift it to the chain level. You find a chain representing this class. Okay. And also let's recall some classical results related to Hochschild homology and Lie algebra homology. So as I mentioned that the Hochschild homology of a universal enveloping algebra of Quillen's model, well, actually, it's also isomorphic to the Lie algebra homology with coefficient of UAX. Okay. And moreover, we have the Hochschild cohomology, right? So Hochschild cohomology. So more precise is Hochschild cohomology with coefficient of UAX. So it's not the dual of Hochschild homology. It's actually the Lie algebra cohomology with same coefficient, UAX. Okay.
So
now we are in a good place to.
Yining, when you say when you use UA of X, can I think of that as chains on the base loop space of X?
Yes, I think they have this identification.
Okay.
Yeah.
Yeah. So in some sense, I think this result that Hochschild homology of chains on the base loop space is the homology of the free loop space. That's due to Goodwillie, right? Or
yes. So I think
Jones,
probably
Jones was the
I think there's lots of way to, I mean, at least to get this result. I mean,
okay.
So yeah. So the way I understand is that Jones actually did for at least on the cohomology side. So actually they press
exactly
the cohomology of S1, at least the cohomology of S1 equivalent to S1 equivalent cohomology of free loop space equals to the like something like a negative cohomology of not UAX but some co-chain model. And actually the second paper, what I mentioned here, the paper of Jones and McLeod, they actually prove some identification of the negative cyclic homology of a co-chain model and the cyclic homology of the Kobar construction of the dual of that co-chain model. So
yes, that sounds right.
Yeah, probably like I can explain that in detail after talk. It's a lot, but I think there's another way to realize that result. There's lots of paper about this similar result.
So by something Manuel said, so I was thinking, I thought that like, so A of X is a Lie algebra. Is it true that the homology of A of X is the homotopy groups of X, or is it the homology of X?
No, homotopy group.
Homotopy groups. Then I would have thought that
It
the
depends what you
homology of
mean.
U of X would be the homology of X, not the base loop space.
No, I think it depends what you mean by homology of A of X, right? There's
So it's a Lie algebra homology. And
the Lie algebra homology of A of
the
X.
Lie algebra homology gives you the homology of space.
Yeah, and that the actual homology, the underlying, like take the Lie algebra, forget it's a Lie algebra, take its homology.
Yeah. So the underlying, the homology of underlying chain complex gives you the homotopy after a shift. Give you the homotopy groups.
Oh, and wait, then you have. Oh no! I agree with your statement. I was confusing things. Everything is fine.
A of X is the primitives of
Yeah, and then I was somehow wait. So are you saying that when you said that the homology of U of X is the homology of the base loop space, you're just saying like view U of X as just like a chain complex and take homology, or were you saying some fancier kind of homology?
No, that's what I meant.
Yeah, I think just the homology underlying chain complex.
Yeah.
Okay. And then how do you? Okay. I'll think about it. Whatever. It's some basic factors, nothing to do with your talk, and just is like, do I remember rational homotopy theory? So I'll just let you continue. Sorry.
Yeah. All right. So and those two results on this slide is just basically like some result just related to the homology, Hochschild homology of universal involving algebra. So you can, at least for this result on this page, you can replace by any Lie algebra. Yeah, it's always work. So okay, so we have this thing, and now let's recall a theorem by Felix Thomas and Victoria. So what they did is that I will not state their result precisely, but roughly you can think about, as I mentioned, that this top class, or you can realize it is a class on the Lie algebra homology, and also you can lift it to a chain level, and you can cap this, at least this class on the Lie algebra, this Chevalier-Amber cochain. It actually will give you isomorphism between the Lie algebra cohomology and the Lie algebra homology, both of them with coefficient on UAX. And what they show is that, okay, on the left-hand side, you have a cohomology theory. Actually, they have its cup product, right? On the right-hand side, it is isomorphic to the ordinary homology of free loop space. And what they show is that these isomorphic actually transfer the cup product to loop product. And if you're counting the degree, it also makes sense. It's the cup product on the left-hand side is of degree 0, and then you use this identification, you can show that the loop product is indeed of degree -d. Okay. Okay, so that's their result. Well, we want to use their result, but actually we cannot use that directly. I think if I remember correctly, what they did is they just used some computational tool from the Sullivan model, and actually they proved like a dual version of the theorem we want. So it's not easy to apply their result, and also what we did is totally on the chain level. So now the question is that okay. So how to realize their result? Because on the chain level, their result is very, very complicated. And how to realize their result just directly to a chain level, right? The chain level. And maybe the next question, maybe before I move, is that if you think about here, you can just think about what they do is sort of use the Poincare duality, right? Your manifold. So now, next question we want to ask is that maybe is there a way to realize the Poincare duality to the cochain level or chain level? Okay, so that's actually one of the motivation. I want to mention the results about Lambert and Stanley. Okay, so Lambert and Stanley. They actually provided a finite dimensional cochain model. So what I mean by cochain model is basically, let's say E is a commutative GG algebra, and the homology of its underlying cochain complex computes the cohomology of your space. Okay, and it's also finite dimensional, and it satisfies so-called Poincare duality, or maybe I just mentioned that E is a cyclic algebra. So we have the cochain model, it has Poincare duality on the cochain level, not just on the cohomology level. Okay, so not only is satisfied this Poincare duality, or it is a cyclic DG algebra. Moreover, if we look at its dual, linear dual, so we get a co-commutative DG coalgebra. We can look at its like commutative cobar construction. So let me recall that. It's not very familiar to most people. So on the underlying space, well, you can look at this C, you can quotient by the copy of Q and also shift down degree by 1, okay? And then you look at the freely algebra generated by C bar, shift down by 1. So that's the underlying space. So it is a Lie algebra, a freely algebra. And it has differential. There's 2 differentials. The first differential is just induced by the differential on C. As I mentioned, C is a DG coalgebra. And the second differential is induced by the co-multiplication structure on C. Okay? And because C is co-commutative, you get a differential on the freely algebra. And this is actually, their result implies that this is actually a equivalence model of for X, okay? And now actually we just use this. We just use this freely algebra, and it should be semi-free DG algebra to be our equivalence model, okay? And we also need to look at its universal enveloping algebra, but as everyone knows that the universal enveloping algebra of a freely algebra is just a tensor algebra. And what is the tensor algebra of the same construction? If you replace the freely algebra by tensor algebra, you just get the associative cobar construction. So that's the ordinary cobar construction people mentioned. All right, that's great. So now the universal enveloping algebra will just be a semi-free DG algebra, okay? And now what we need to do is that we need to compute its Hochschild homology and cohomology. And because it is a semi-free DG algebra, there is a very, very small resolution can help you to compute its Hochschild homology and cohomology. It's very easy. It's very good chain or co-chain complex. And also, let me just move to the next page. And also because of this Poincare duality, we just do some computation. We will get a duality on the Hochschild, between Hochschild homology and the cohomology. So let me use this. It's pussy. Actually, this cyclic algebra condition implies that. We have a duality between the Hochschild homology and cohomology. Actually, we proved that on the chain level. And actually, this duality is the same as the duality provided by Felix Thomas and Victoria. So, yeah. So we have a non-commutative Poincare duality between the Hochschild homology and cohomology. And actually, if I apply their result, and also the result by Jones I mentioned before, so what we get is actually we get an algebraic model of the string bracket. So again, we use a reduced version, so it's related to reduced cyclic homology. Just you quotient the copy of K or copy of Q on each even degree. So let me write down this formula. Yeah, it's a long formula, so I will write it and mention, explain that. Yeah. So this is actually an algebraic model for the string bracket. Right. So basically, B and I, B is related to M, I is related to E. Actually, this pussy actually intertwining the loop product with the cup product. right? So you pick two class on the cyclic homology, you use B map to Hochschild homology, and use Pussy inverse, you send back to the Hochschild cohomology, take the cup product, and then send back to the Hochschild homology, then send back to cyclic homology. So this actually gives you an algebraic model for string bracket. So I don't want to mention this is as a theorem, even though we do give an argument in our paper, but I think this probably is already well known to some expertise. So, all right. So that's the end of second part. So we do have the algebraic model for string bracket. Any questions?
Yes.
Sure.
Why did you dualize your Poincare duality model? You could have just taken Hochschild chains on E, on what you called E.
Yes, but probably this will give you something related to the cohomology of free loop space or something like that. Probably not exactly, but yeah. I think the Hochschild homology and negative cyclic homology of E will probably give you the cohomology of, or S1 equivalent the cohomology of the free loop space.
Right. Right. So, I mean, but why did you go through this process of dualizing and not just
I want to get a Hochschild. So that's basically, I want to apply this statement, right? So that's, I want to get that. Actually, this is basically what I mentioned, why I want to mention the result of Jones and McClear. Yeah, they do that for co-bar construction of the dual of your co-chain model. So that's their result. Yeah.
Right, I see. But I was just saying that you could have just taken Hochschild chains of E, Hochschild homology of E, and then work with the cohomology of the free loop space. Or do you absolutely need to work with the homology of the free loop space?
Then what do we get first? If we do cohomology, then you need to transform the product to co-product, right?
Yes.
Oh, I did not think about that.
But then you don't have to go through all this, like taking universal enveloping algebra and so on. There's a direct formula for the co-product, for the loop product, but now as a co-product in cohomology, and you can work with that as well.
Okay.
Yeah.
Well, this is basically, we did not think in this way because there's also other side, we need to have the decomposition. And actually our decomposition can only be done for the universal enveloping algebra for like DG algebra.
I see, okay.
So maybe let me, I don't have enough time, so probably I need to move a little bit faster. Yeah. Yeah, so that's the second part. Let me talk about the third part. Do we have a model for the decomposition? Maybe I just can briefly talk about. So yeah, so this can partially answer your question, just why we are just want to use the universal enveloping algebra. Well, it's basically related to our work before. It's actually about this dual Hodge decomposition. So let me just talk about this decomposition, maybe just write it here. I probably don't have enough time to explain that. That's okay, maybe we can explain that after talk. Yeah. So actually, this works for any universal enveloping algebra. So but I will just use the Quillen's model. So for the reduced cyclic homology of UAX, we have this decomposition, and also on the Hochschild homology and cohomology, we have the similar decomposition. So just briefly talk about what is this decomposition. So the decomposition of Hochschild homology and cohomology side, if you remember the early statement, I mentioned that those are related to the algebra homology or cohomology of coefficient of UAX, and this basically just induced by the PPW decomposition on your universal enveloping algebra. Okay. And the first decomposition, there's two ways to think about. You can also think about it's related to PPW decomposition, and another way to think about that is that this cyclic homology of UAX, as I mentioned, this UAX is cobar of C. Okay, it's related to the negative cyclic homology of C, which is due to the cyclic homology of E. And because E is a commutative DJ algebra, there is a Hodge decomposition. And this transforms to a dual decomposition on the negative cyclic homology of C. And this can be identified with this decomposition on UAX. And okay, so based on this decomposition, we have the, let's recall some earlier result. So some theorem, okay, by Berest, Ramadoss, and myself, is that, well, recall we do have an algebraic model which involves B, I, pussy inverse. So this B map actually will decrease the Hodge degree by 1, and I map will preserve the Hodge piece, Hodge degree. And moreover, both pussy and pussy inverse, they preserve the Hodge degrees. Okay. And then the next theorem we want to mention is that, all right, so I haven't mentioned about the relation between OR decomposition and the decomposition in string topology or in just in topology. Actually, or dual Hodge decomposition on cyclic homology can be identified with the homology on reduced S1 equivalent, the P-1 piece on the reduced S1 equivalent homology of free loop space. All right, so that's the result we had, maybe we have or we had before. And well, right now, if we just go back to this formula, we know how to identify this. We have the algebraic model of a string bracket. We have the algebraic model for those decomposition. We know how it works with respect to all those maps. So the only thing left is this cup product, right? That's the only thing left. So let me just state that's actually our main result. So I don't think I have any time to just talk about why the proof or the idea of this main result, but let me just state that. The main result, again, by Yuri, Ajay, and myself, is that, well, again, let me just state all the conditions we need. X is 1 connected, closed-oriented manifold, of rationally elliptic homotopy type. So, okay, homotopy type. And we have the decomposition on the Hochschild cohomology of the equivalence model, a universal enveloping algebra equivalence model. So the main result is that actually the cup product preserve the Hodge piece. All right. And then we just use the, okay, so let me just finish the talk by. So this theorem has a corollary, basically, well, it's just on the cyclic homology side, right? So look at this piece on cyclic homology and the Q piece. So remember that we have first the B map will decrease the Hodge piece by 1. So we have 2 B maps, and then the rest of them, they all preserve the Hodge piece. This actually will be end up in P plus Q minus 2. Okay. And that's basically just this result and other results we mentioned here and this formula. Okay. Did I miss? Oh, I think I lost one page. I don't know why. Oh, yeah. I think I swapped the order. Yeah. So now use this this result, and again by this identification between the Hodge piece on the algebraic side and the Hodge piece on topology side, we will get. Let me just recall our main result. So we will get our main result. Basically, what I state at the very beginning of the talk. Is that on the as when you graph homology of free loop space, you have this P plus Q minus 1, because well, on topology, a piece will be identified with P plus 1's piece on algebraic side. So that's why you will get P plus Q minus 1. All right, I think that's the good time to stop.
Well, thank you, Yining.
Yeah.
We can try clapping again. I don't know. Everybody's on mute anyway.
There's a button on Zoom. No.
Thank you. Are there any questions?
Have you thought about other operations?
What do you mean, like the Gerson-Haber bracket or something?
Yeah, for example, Gerson-Haber bracket. There's also the Lie algebra in cyclic homology is part of a Lie bialgebra.
Oh yes, so I know. So Lie algebra, I was saw that before, but I don't know. I haven't seen.
I think in that case, the co-bracket does not preserve the Hodge.
Yeah, it's probably the different argument, right? I mean,
yeah, but that, I think that means something interesting. You can ask Florian more about that.
yeah, and I'm saying maybe about Gerson-Haber bracket is that when we prove like where it is, I swap the order of at least 2 pages. So when we prove this theorem, we also need to use lots of. So this Hochschild cohomology will be identified with other like direct sum Hochschild cohomology, and then there's certain identification. And I think on Hochschild cohomology, there are more isomorphism of algebra other than like isomorphism of Gerson-Haber algebra, right? So I don't know about the loop bracket. Yeah, I don't know. Yeah, at least what some result we use is only isomorphism of algebra instead of isomorphism of Gerson-Haber algebra.
Could I ask a very basic question from some part in the beginning when you defined the Hodge decomposition?
Yeah. Do I need to go back?
Yeah, I just wanted to see that slide again. So in that definition, are you saying that any n to the p is an eigenvalue, or are you just decomposing it into all these possibilities? And
so you just look at for each n, you look at the eigenspace with eigenvalue n to the p, and then you intersect them. That's what I think.
So how do I know that all the eigenvalues are integral and positive or something?
Well, I don't know on the topology side. I think they probably also do this for algebraic side, and this have some combinatoric interpretation about this operation. I think probably, yeah.
And I mean, you could also decompose it further, I guess, into not just all the p's, but all the n's. Or is it?
No.
Oh no, you take the intersection. I'm a bit confused about the.
So you fix p's and n is changed. You run any n, every n, and look at this.
Oh, but then you also say that it's okay. All the psi n's are different. You just
right. So for each n, you look at eigenspace with eigenvalue n to the p, and p is fixed, n is changed.
Okay, and so you're saying that I don't know what you're saying. Okay, but it gives a decomposition this way. Interesting.
Yes, that's their work. I think I can understand on the algebraic side, not really topology side. Yeah, algebraic side is just some combinatoric stuff.
Yeah, that'd be interesting maybe for me to understand. Maybe is there one more question for Yining?
I have more, but maybe for after the.
Yeah, maybe you can talk.
Yeah, we can talk like I still have time.
Yeah,
I need to teach at 11 and in my time, so I still have plenty of time. Yeah.
If nobody else has a question, let's thank Yining again. We're very happy that you. Oh, there is a clap emoji. That's reaction.
Yeah.
Let's just do that.
I saw that.
Well, so thank you so much for preparing this and giving us this talk.